OMG, hey, what's up? I haven't heard from you in like forever. What's the tea? What's the goss? No way, that's like actually so funny. Like I'm actually LOLing right now. Wait, hold on. There are like some kids here that are waiting for me to like teach them about solving systems of equations or whatever. Can I like call you back? Yeah, they're just like staring at me. It's like super creepy. No, I don't think they're gonna like hurt me or anything. They're just like really weird, you know? No, yeah, they're like so annoying. Like, don't even get me started. But listen, let's catch up later, okay? OMG perf. OMG stop. No, you're the best. No, you hang up. Okay, love you, mean it. Bye. How rude of me. You weren't supposed to hear that. So sorry about that. Hi, friends. Welcome to our fourth class of Unit 5, where we will be continuing our discussion of solving systems of equations using this method we call substitution. So remember, if I want to solve a system by substitutione, our goal, what is it that I'm trying to do? Kind of two parts to the method to the madness here. What's my strategy? Go ahead, 30 seconds, remind me. Okay, very good. So, if I want to solve a system of equations by substitution, the first thing that I need is to get something containing a variable by itself. So I need to begin by isolating a variable term in one of my two equations in my system. Once I've got a variable or something containing a variable isolated, then the idea is that I should be able to substitute into my other equation and use that to find the value of my variable, and then I can use that to find the value of the last variable. Very nice. Now, if we up the ante a bit, though, perchance you noticed that last time we chatted, all of our systems had at least one equation where one of its variables didn't have a coefficient. In other words, it had a coefficient of invisible 1, which we could easily get by itself and substitute in. So naturally, we arrive at today's question: what can we do if none of the variables in either of our equations has that nice coefficient of 1? So sometimes, not always, but sometimes, we'll end up in a position where we can actually substitute a variable with its coefficient. For example, take a look at this guy. 3d equals 18c minus 33. Negative 2c minus 3d equals negative 7. What do you think I can substitute in here and where? 10 seconds, pause the video. What looks substitutable? Alrighty, you see that 3d there? I do. Because I have the same thing, the variable with the same coefficient in both of these equations, whenever I see a 3d in the bottom equation, I can plug the equivalent statement of 18c minus 33 in from the top. Cool. So in this case, I can substitute in not just a d, but 3d. So using substitution here, I can show that negative 2c minus 3d, which from our first equation we know is equivalent to 18c minus 33, is equal to negative 7. If you haven't already gotten this far, pause the video, take 2 minutes, solve for c, and then use that value of c to find d. Go! All right, let's do it. So I'm going to take my negative sign and start by doing some distributive property. So negative 2c minus 18c plus 33, just flipping both of my signs, is equal to negative 7. From here, I've got some like terms I can combine. Negative 2c minus 18c, well, that's negative 20c plus 33 is equal to negative 7. Minus 33 from both sides to get closer to having c by itself. That shows me that negative 20c is equal to negative 40. Would you look at that? That's a number that evenly divides by negative 20. Negative 40 divided by negative 20 is positive 2. Now that I know that c is equal to 2, I'm going to substitute into one of my two equations to find d. Thinking cap, which equation is probably strategically wiser to plug into? 10 seconds, go. 5, 4, 3, 2, 1. It wasn't 10 seconds, but who cares? So I'm going to take this guy. Notice in the top equation, remember my goal now is to get d by itself. The top equation is closer than the equation on the bottom to having d by itself. So I'm going to use the one on top. You could absolutely use the one on the bottom. It does not matter. So here, I'm going to take 3D. It is equal to 18C. C we've said is equal to 2 minus 33. Cool. 3D is equal to 18 times 2, which is 36. 36 minus 33, well, that's equal to 3. Dividing both sides by 3, that tells me that D is equal to 1. Fantastic. So C is 2, D is 1. Totally welcome to leave our answer here. That's great. If I wanted to, I could write this as an ordered pair. 10 seconds. How would I write this as an ordered pair? Go. And stop. Alrighty, well, I don't want ordered bananas. I want ordered pairs, and ordered pairs are arranged alphabetically. In this case, C comes before D in the alphabet, so in our ordered pair notation, the 2 is going to come before the 1. Very nice. Cool. Let's try another. 8x minus 5y equals 24. Negative 9y equals 40 minus 8x. Do you see anything that looks nice and substitutable? If you do, can you get it by itself? Plug it into the other equation, find your variable, and use that to find your last one. Take 2 minutes, pause the video, see how far you get. Go ahead. Okay, well, if you are like me, then you probably noticed that 8x shows up in both of my equations. So I'm going to get 8x by itself in one of these two. I think it's easier to get 8x by itself in the equation on top. You could absolutely do it for the one on the bottom. Mathematics is all about choice, doesn't really matter. So 8x minus 5y, I know is equal to 24. I want to get 8x by itself. Let's add 5y to both sides. So that tells me that 8x is equal to 5y plus 24, or 24 plus 5y, it doesn't really matter. Now that I know 8x is equal to 5y plus 24, anytime that I see an 8x in the second equation, I can substitute in. So that tells me here by substitution, negative 9y is equal to 40 minus 8x, but 8x is really 5y plus 24. Cool. Doing some substitution, I'm going to take my minus sign. I'm going to distribute. Negative 9y is equal to 40 minus 5y minus 24. Combining some like terms, 40 minus 24, I know how to do that. That's 16 minus 54. Let's move our y's over to the left side here. So I'm going to add 5y to both sides to get negative 4y is equal to 16. Last thing standing between me and y by itself is that pesky little negative 4. Dividing both sides by negative 4, I get y is equal to negative 4. Now that y is equal to negative 4, I'm going to plug into one of my original equations to get the value of x. Thinking caps, where is strategically the wisest place to plug in here? 5, 4, 3, 2, 1. Again, it doesn't really matter. For me, my goal is to get x by itself. Notice that this rearranged top equation is pretty close to having x by itself. I'm going to choose to plug in there. So I've got 8x is equal to 5y, but we know that y is equal to negative 4, and then I have a plus 24 at the end. Simplifying, 5 times negative 4 is negative 20. Negative 20 plus 24 is equal to positive 4. And dividing both sides by 8, we find that x is equal to 4 over 8, which reduces to 1 over 2. As an ordered pair, I would write this, of course, as 5, 4, 3, 2, 1 half, comma negative 4, right? X comes before y in the alphabet, so the 1 half is going to come before the negative 4 in our ordered pair notation. Very nice. So sometimes we will find ourselves in a situation like this where I can plug in a variable with its coefficient, but sometimes we won't be so lucky. Take this guy, 2m minus 12n equals negative 14, 5n equals 10m plus 15. Notice here, 2m, 10m, not the same coefficient. 5n, 12n, not the same coefficient. So I might need a different approach. What do you think I might be able to do here? Take a risk, take a chance, take 30 seconds. I still want to be able to substitute. How can I make a choice to accomplish that goal? Go. Alrighty. So if I can't plug in 5n, for example, looking at this bottom equation over here, I can't plug in 5n to the top equation, but if I could get n by itself, I could plug in n. Well, to get n by itself, I could divide by 5. So taking this equation, remember, I can make any choice I want to any equation in my system as long as I do it to both sides. So I'm going to divide both sides of the bottom equation by 5 to get that n is equal to 2m plus 3. And now that n is equal to 2m plus 3, well, I can take that 2m plus 3 and plug it in for the n in my first equation. Cool. So by substitution, I can show that 2m minus 12 times n, but n we've just shown is the same as 2m plus 3, which is equal to negative 14. Now all I've got to do is solve for m. Take 2 minutes, pause the video, solve for m, use that value to solve for n. Go. Alrighty, so I'm going to do some distributive property. Negative 12 here is going to get distributed, kind of a big number, but that's fine. 2m minus 24m. Negative 12 times 3 is negative 36, which is equal to negative 14. From here, I've got some like terms. 2m minus 24m is negative 22. m minus 36 equals negative 14. I want to get m by itself. Let's add 36 to both sides. First, again, reverse order of operations, addition and subtraction before multiplication and division. So I'm going to add 36. I get negative 22m. It's equal to 36 minus 14, which is 22. Wow, it's almost like I wrote the problem to have nice numbers in it. Look at me, I'm so generous. Dividing both sides by negative 22, m is equal to negative 1. Now that I know m is equal to negative 1, thinking caps, where is the wisest place to plug this value of m back in? 5, 4, 3, 2, 1. Again, you can pick anywhere you want. I'm personally going to pick right over here. Notice I want to get n by itself. N is already by itself in that equation where I divided by 5. So here, I can show that n is equal to 2 times m. m we've shown is negative 1 plus 3. So that means n is equal to negative 2 plus 3, which is equal to 1. m is negative 1, n is 1. If I wanted to write this as an ordered pair, how would I do it? 5, 4, 3, 2, 1. Well, m comes before n in the alphabet, so as an ordered pair, the negative 1 would come before the 1 in our ordered pair notation. Very cool. One more for the road. 3a minus 2b equals 11, 4a plus 3b equals 9. Let's solve this guy by substitution. So, my advice to you would be, try and find the number, because we're going to have to do some division, that will give you maybe the nicest things after you divide. However you want to interpret that. Alrighty. So for me, the piece of advice that I like to give, I know if I need to get a variable by itself, in the top equation, either I need to divide by 3 or 2. In the bottom equation, either I need to divide by 4 or by 3. There are two approaches to this. One approach would be, dividing by 2 is probably the easiest thing, but dividing 3 by 2 will give us a fraction. Dividing 11 by 2 will give us a fraction. In the bottom equation, dividing by 4 will give us 2 fractions, 3 divided by 4 and 9 divided by 4. But notice that if I divide by 3, even though 4 over 3 will be a fraction attached to a, 9 evenly divides by 3. So I personally, when I'm solving by substitution, like to choose the variable that when I divide by its coefficient will give me the fewest amount of fractions. So I'm going to choose in this equation, the bottom equation, to get b by itself. So my opening move, and again, you can make any opening move you want. This is not the only way to solve this problem, but the more of these you solve, the more you start to notice these kinds of patterns. In this case, notice I'm going to have to divide by 3 to get my variable by itself. Dividing negative 4 by 3 is going to give me a fraction. Negative 4/3 a. Gross. But 9 divided by 3 is 3, which is a relatively nice number to work with. Cool. Now I've got b by itself. I solved for b in the second equation, so I'm going to plug it back in to the equation on top. So from here, that tells me that 3a minus 2b, but we just showed that b was the same as negative 4/3 a plus 3 is equal to 11. From here, doing some distributive property, 3a, negative 2 times negative 4/3, you can feel free to fact check me, is positive 8/3 a. Negative 2 times positive 3 is negative 6, and then I carry down my equals 11. From here, I've got some like terms I need to combine. 3a plus 8/3 a. Gross, but doable. Again, I need a common denominator, so I've got 3 over 1 plus 8 over 3. I need to rewrite 3 as something over 3. Well, 3 over 1 is the same as 9 over 3, and 9/3 plus 8/3 is 17/3. Cool. So I've got 17 over 3a. Ew, but sure. Minus 6 equals 11. I need to get a by itself. Let's add 6 to both sides. So I'm going to add 6. That leaves me with 17 over 3a is equal to 17. Interesting. From here, I need to get a by itself. I could divide by 17 over 3, which is the same as multiplying by the reciprocal of 3 over 17. Over here, notice 17 is 17 over 1. So I have 17 over 1 times 3 over 17. Of course, on the left side, these undo each other. 17 on top, 17 on bottom. These also cancel out. That leaves me with 1 over 1. I have 1 over 1 times 3 over 1, which is 1 over 3. That's just 3. And I'm left with a on the left. Would you look at that? A equals 3. Thinking cap, where is the wisest place strategically to plug this value in for a? Go. 5, 4, 3, 2, 1. Well, that would probably be right over there. So now that I know a is equal to 3, I want to find the value of b. So b is equal to negative 4/3 a. A is equal to 3 plus 3. From here, negative 4/3 times 3. Well, again, this is 3 over 1. My 3's are going to undo each other. So this is negative 4 times 1, which is just negative 4, plus 3. That means that b is equal to negative 1. Cool. A is 3, b is negative 1. If I wanted to, how would I write that as an ordered pair? 5, 4, 3, 2, 1. Well, a comes before b in the alphabet. Therefore, in our ordered pair notation, 3 would come before negative 1. Fantastic! You now know how to solve any system of equations in two variables by substitution.